inclined or skewed supports. In the preceding sections, the supports were oriented such that the resulting boundary conditions on the displacement were in the global directions x and y. If a support is inclined or skewed at angle alpha from the global x-axis, so this is, I have an inclined support has an angle alpha with the x-axis, this line parallel to that, so it is angle with the x-axis. Here the boundary conditions of the displacement are not in the global directions, but on the local coordinates x dash, y dash. So we need to perform a transformation of the global displacement at node 3 only. Again, we need to make or to do a transformation of the global displacement at node 3 only into the local coordinates or the local directions x dash and y dash, while keeping all other displacement in the x, y global system, while the others nodes keeping in the x, y coordinates. So I will do the transformation for node 3 only that has inclined supports. We can then enforce the zero displacement boundary conditions in the force displacement equations and finally solve the equations in the usual manner. Then we can put or assume the zero displacement boundary conditions in the force displacement equations, as you know, and then we can solve the equations in the traditional manner. Okay. The transformation used is analogs to that for transforming a vector from local to global coordinates. Again, we need to transform from local to global coordinates. For plane truss, here we are talking about plane truss, that's mean not in three-dimensional coordinates. We can use equation 16 here, you can see here. Now I have u dash v dash, this is local, multiplied by t transformation matrix multiplied by d displacement. So here d displacement is the matrix for the global one, and here for the local one. Again, we will deal now with the node 3 only. That means we will deal with the nodes that has an inclined supports and a skewed supports. Now u3 dash v3 dash, this is came from equation 16, is equal to cosine alpha sine alpha, because I have angle here, minus sine alpha cosine alpha u3 v3. Again, we deal with the nodes that has an inclined supports, skewed supports. Now if we rewriting equation 9.1, so this is the d3 dash local one equal to t3 transformation matrix related for node 3, again for node 3 only, multiplied by the displacement d3 for the displacement related for node 3 only. Here t3 is equal to cosine alpha sine alpha minus sine alpha cosine alpha. Now write the transformation for the entire nodal displacement vector as. Now if we are talking for the all nodal displacement, that means d dash equal to t1 multiplied by d, or d is equal to t1 transform multiplied by d dash. If you remember here, t1, the transformation matrix transpose, is equal to the transformation matrix inverse. So we put instead of inverse transpose. Now here we can get the d displacement from transformation matrix multiplied by the d displacement local coordinates, from local to global, where the transformation matrix for entire truss, it is equal 6 by 6 matrix. So the size of the entire truss, it is 6 by 6. That means I have 6 rows multiplied by 6 rows and 6 columns. So T1 is equal to I 0 0 0 I 0 0 0 T3. Okay, now you can see here T3, that means it's cosine alpha minus sine alpha, and minus sine alpha cosine alpha. So you can see the transformation is done here, just here. I will not take the transformation for all not just for node 3. Now each submatrix here, this is submatrix, okay, in equation 9-6, the identity matrix I, this is identity matrix, and the null matrix is 0, and the matrix T has the same 2 by 2 order. So this is 2 by 2 order, this is 2 by 2, this is 2 by 2, and so on. That order in general being equal to the number of degrees of the freedom freedom at each node. To obtain the desired displacement vector with the global displacement components at node 1 and 2, local displacement component at 3, we use equation 5 here to obtain equation number 7. So here you can see we are talking about all nodes. Now you can see this is the transformation from local to global, local to global, local or to global. Equation 7. Now you can see U1 V1, U2 V2, U3 V3, and here I have the transformation matrix. So you can see this is identity, this is null, submatrices, and here this is null matrix, that means 0 matrix, and so on. And you can see here the transformation T3, this transpose depends on equation number 7, number 5, according to equation number 5, because I have T1 is transpose. In equation 7 here, we observe that only node 3 global components are transformed. Now you can see just node 3, okay, global components are transformed. Okay, yeah, while all the other no, still the same. Okay, just here for node 3 are transformed from local to global, Why? Because I have here the transformation matrix. This is for T3, this is for node 3 only, as indicated by placement of the T3 transform matrix. We denote the square matrix in equation 7 by T transpose Okay, now we denote the square matrix in equation 7 by T T1 transpose. Okay, T1 transpose. In general, we place 2 by 2, okay, 2 by 2 for T matrix in the T1. Wherever the transformation from global to local this is needed, where skewed supports exist. Upon considering equation 5 and 6, we observe only node 3 components of D, okay, are really transformed to local axis or local skewed axis components. Again, that's mean from all these equations, okay, especially for equation number 7, we transform just the skewed axis component, okay, while the other nodes keep all as it is. This transformation is indeed necessary whenever the local axis x dash y dash fixed direction are known. Furthermore, the global force vector can also be transformed by using the same transformation T or D dash. Now you can see here, and if we are talking about global force, okay, we can transform from global to local by the transformation matrix. In the global coordinates, we then have F is equal to K multiplied by D. This is in global. This one is in global. Pre-multiplying equation 9 by T1, we have so when we multiply equation 9 by T1, that's mean when I multiply equation 9 for both sides, now I get equation 10. Now you can see the matrix T1 transformation matrix. Okay, this is T1 multiplied by F, yeah, equal to T1 multiplied by K stiffness matrix multiplied by displacement matrix. Now for the truss in the figure 23 here, the left side of equation 10, the left side, this one for equation 10 is, now you can see this is T1, this is the transformation matrix T1, and this is the force matrix. Now you can see it is equal to F1x, F1x, F1y, F2x, F2y, F3x, F3y. Now you can see when I multiply this matrix by that matrix, I will get the right hand of the equation. It is equal to F1x because this is identity matrix. That's mean 1 0 0 1, and here it is 0 0 and so on. So here there is no difference. 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 While here there is a difference. Why? Because when I multiply the transformation matrix T3, that's mean cosine alpha, sine alpha, and so on, multiplied by that, I will get the local nodal forces for node 3, and here I have the nodal forces for in the y dash, in the y direction for node 3 only. Now, where the fact that the local forces transform similarly to equation 9.2, as now you can see here, the force for node 3, it is equal, this is in general, the local force for node 3 is equal the transformation matrix for node 3 multiplied by the local forces for node 3 in the global coordinates. now has been used in equation 11. So here this equation 2 have been used in equation 11. From equation 11 we see that only node 3 components of the force have been transformed to the local axis components as desired. So now we can note that only the components of node 3 have been transformed from local have been transformed from global, now you can see this is global, to local coordinates. Now using equation 5 into equation 10 I will get equation 13. Now you can see this is T1 transformation matrix T1 multiplied by the local by the nodal displacement in the global is equal to T1 multiplied by K multiplied by T1 transpose multiplied by the displacement in the local coordinates. This is when I use equation 5, put it in equation 10 here. Now using equation 11, this one, we find that the form of equation 13 becomes f1x. Now look well, this is here we are talking about the forces in the global directions, f1x, f1y, f2x, f2y, f3x dash, or say f dash 3x and f dash 3y equal to T1 K T1 transpose multiplied by the displacements, say E dash. Now you can see here when I use equation 11, this one, okay, we find that the equation 13, this one, will be as equation 14. So equation 14, this is the most important equation that we use it, or that we need it to solve the problems that have, inclined, or that we call skewed supports. Okay, so again equation 14, this is the most important equation that we needed to solve the equation the problems that has inclined supports. Again, now you can see here, this is the global forces and this is the displacement forces, and here we have the transformation matrix multiplied by the stiffness matrix global. Now, as U1 equal to U1 dash and V1 equal to V1 dash and U2 equal to U2 dash and V2 equal to V2 dash, and from equation 7, this one, and equation 14, okay, is desired from that allows all nouns global and inclined boundary condition to be enforced. The global forces now result in the left side of equation 14, this is the global forces. To solve equation 14, to solve this equation, first perform the matrix triple product. First we need to solve or to do the triple product of these different matrices T1 K multiplied by T1 transpose. Then invoke the following boundary conditions for the truss in the figure 23. Now U1 is equal to 0, V1 equal to 0, and here V3, this is equal to 0, V1 equal to 0, U2 V2 it is not equal to 0. put this in your mind because maybe can move. While v3 dash in the y dash it is 0. That means this cannot move in this direction, cannot move in this direction, while can move in the x-axis again. Now you can see v3 dash that means cannot move in the y dash, while can move in the x dash. So now you can see u3 is not equal to 0, u3 dash is not equal to 0 to 0. Now then substitute the known value of the applied forces F2x along with F2y equal to 0. Now you can see here F2x it is applied, okay. F2y equal to 0. I have no force at node 2 in the direction of y, and F dash 3x is equal to 0. I have no force here. I have no force. F dash 3x, there is no force. Into equation 14, here I will put here. So I can get, or I can solve the equation 14. Finally, partitions the equations with the known displacement here, equation 1 and 2 and 6 of equation 14. Say here equations 1, 2 and 6 of equation 14, and then simultaneously solve those associated with the unknown displacement u2, v2 and u dash 3. After solving the displacement, return to equation 14 to obtain the global forces and the inclined ruler reaction F3y. Again, now when I put, that's mean u1 v1 equal to 0 and v3 is equal to 0. Now you can see u1 equal to 0, v1 equal to 0, u1 is equal to 0, v1 equal to 0, and this one equal to 0. So I will get u2 v2 u dash 3. Okay, in that case I have 3 unknown equations and three equations with 3 unknown, so I can solve them, and then I can get the forces F1x and F1y and the F dash 3y. Example. For the plane as shown in figure 24 here, determine the displacement and reactions. Let E is equal to 210 gigapascal. The cross-sectional area is equal to 6 multiplied by 10 or minus 4. This is minus, again this is minus, m squared for the elements 1 and 2. And A is equal to 6 multiplied by under square root 2 multiplied by 10 power minus 6. This is minus again. This is minus, please. M square for element 3. So now he wants the displacement and the reactions for this plane truss, where the modulus of elasticity for element 1 and 2, this is element 1 and 2, is equal to 210 gigapascal, and the cross-sectional area for element 1 and 2 is equal to 6 multiplied by 10 power minus 2 meters squared, and the cross-sectional area for the element 3, it is equal, for element 3, this one is equal to 6 multiplied under square root 2 multiplied by 10 power minus 4 meters squared. This is for element 3. Now solution. We begin with the using equation 3 for 23, this one. Okay, again, why? Because I have bar element. I have bar element, and this is, and this one in general. okay, for arbitrary oriented. Do not forget that. So for element number 1, I will use equation 23. This is the stiffness matrix for each element that oriented, that in general, okay, this is the stiffness matrix for element that arbitrarily oriented. Do not forget that. So now if I take the the x-axis here, the x-axis is the reference, so the direction from the x-axis counterclockwise, I will use it as a positive direction. So if I move from x, okay, to equation number 1, so the angle is equal to be 90. Again, this is the reference, this is my reference, this is my reference. So the angle from the x-axis to the element, from the x-axis to the element number 1. So it is the angle will be 90 degree. Cosine theta is equal to 0. Sine 90 is equal to 1. I will put all these data in the equation 23 here. Okay, and do not forget that. And the direction, okay, the direction from 1 to 2. The direction from 1 to 2. So I have u1 v1 u2 v2, u1 v1, okay, and here it is u2 v2. I will repeat the same step for element 2. For element 2, this is element 2. Now you can see, okay, this element is parallel to x-axis, so its equation is equal to 0. So cosine 0 is equal to 1, sine 0 equal to 0, and the direction from u2 to from node 2 to node 3, the direction from 2 to 3. So now you can see it is u2 v2 u3 v3, and here I have the cross-sectional area and the modulus of elasticity, and this is the length. This is the length of the element. Okay, the length of elements are denoted on the in the figure. Now for element 3, this is element 3, the angle is equal to 45. So I can get the length of element 3 by using Pythagoras theorem. Again, now the equation here is equal to 45. Cosine theta is equal to 0.707. Sine theta is equal to 0.707. I will put all this data in equation 23. Here I have the cross-sectional area. Here, this one, the modulus of elasticity, and this one is the length of the element. So I have here the 3 elements. I need in the next step to calculate the total stiffness matrix. The total stiffness matrix. Actually, now you can see this is the total stiffness matrix. You can see u1 v1 u2 v2 and u3 v3. Okay. Do not forget this is the figure. Now we obtain the transformation matrix T1 using equation 6. Do not forget this is T1 equation 6 to transform the global displacement at node 3 into local nodal coordinates x dash y dash. So I need to use equation 6. This is the transformation matrix to transform the global displacement at node 3 into local displacements at the local coordinates x dash y dash. In using equation 6, okay, the angle alpha is equal to the angle alpha. Do not forget here I have cosine alpha sine alpha minus sine alpha cosine alpha, so that the angle is equal to 45. Now you can see here this is cosine alpha sine alpha minus sine alpha cosine alpha. This is the T1. Now next we will use equation 14. Okay, next we will use equation 14. In general, we would use equation 13, okay, to express the assembled equations. Now first define the K is equal, K, the stiffness matrix, okay, is equal to T1 multiplied by K multiplied by T transform, T1 transform. Okay, so I need to define the K total. Again, now you can see here, this is T1 multiplied by K. So when I multiply T1 multiplied by the stiffness matrix that we have determined previously, okay, now you can see this is the stiffness matrix and this is T1. So I will multiply T1 multiplied by K, I will get equation 21. Equation 2. This is T1 multiplied by the global stiffness matrix. Now, I will multiply this equation by T1 transform this time. T1 transpose. T1 transpose. So this is the result. This equation 22 actually came from equation 21 multiplied by T1 transpose. T1 transpose. T1 transpose. Then again, now I need to use this equation. Notice in comparing K in equation 22 to K from equation 19 that only stiffness terms associated with the skewed at node 3 degrees of freedom at node 3 skewed at node 3 degrees of freedom have changed as expected. That's mean if we when we comparing equation 22, this one, this is 22, with equation 19, we go back to equation 19, this is 22, and this is equation 19. When I make comparison between them, okay, we can notice that only the stiffness terms associated with the skewed node 3 degrees of freedom have been changed. So just with the node 3 have been changed. Now applying the boundary conditions, now if we go back, I have equation 22, okay, this one, and here equation 13. When I use u1 v1 equal to v2 v3 dash equal to 0. Why? Now you can see here in the figure. Okay, now u1 v1 is equal to 0. Here u2 here u2 is equal to 0, or v2 is equal to 0, u2 is not equal to 0, and here I have u or v3 dash is equal to 0. Okay, now you can see u1 v1 equal to 0 and v2 equal to 0 and v3 dash equal to 0 into equation 22. So I will put all these terms in equation 22 here. Okay, so we can eliminate the related columns and rows. In the end, I will get equation 23. Okay, so equation 23 actually is coming from by applying the boundary conditions here. So we can eliminate the rows and the columns. Okay. Now you can see here. I have two equations to announce, so I can get u2 and u3 and u3 dash or u dash 3. Again, when I have these boundary conditions, I put it in equation 14 again to get the unknowns of the forces F1 x, F1 y, F2 y equal to 0, and F dash 3y is equal to 707 kN. Thank you.